Hi ladies and gentlemen, welcome to Lesson 13's pre-class video. What we're going to talk about today is Newton's method, and we're just going to provide a little bit of the background for Newton's method, which we will expand in class. So to start, what we're going to do is take a look at the objectives. We'll go through all of these in class. Today's video is focused on the first one. So what is Newton's method? Newton's method is a means for us to be able to find the zero of a function. What we are after is the input for a function that equates to an output of zero. And the derivation for this comes from the definition of the derivative. We're going to take a look at this definition. Unfortunately, of course, the definition includes the limit, which we can't really do much computation with. So we're going to approximate the derivative here, and what we're going to do is we're going to pick an x value that we are currently located at. So we are at some specific input value for the function, which we call x now. It's where we are right now. And we're going to use the derivative information in order to come up with an improved approximation for the zero that we're after. So keep in mind, we're after this input, x star, which gives us an output of 0. And we're going to set up that x star then as where we are now plus the small change in input. Taking a look at the definition for the derivative here, we're going to make substitutions into the definition, and we're going to remove the limit. Removing the limit gives us an approximation. And we're going to focus on where we are right now and then moving to a better approximation for the zero. So we're going to take this item here and we're going to solve for what we're actually after, which is x star. This is the input, which would give us an output of 0. The question is, how did we end up moving from this representation to this one here? Mostly it was just algebra. However, we're missing an item. There is no function evaluation at x star in our representation here for Newton's method. Why? The reason is because what we are after is the input that gives us an output of 0. So we are going to assume that f of x star is equal to 0, because that's what we're trying to determine, is what is x star that makes that happen. All of this can be a little bit difficult to look at equations and figure out. I do recommend that you go through these equations prior to class, but let's take a look at a picture. Take a look at this image right here, and what I'm going to do is I'm going to shift over to OneNote. Those of you who take notes with your iPad or in OneNote, it's really a useful tool to be able to grab pictures or PDFs and be able to mark them up. So the information that we have where we are right now. We have an x value, an input value where we are currently located. And because we know the function, then we know the output value. And what's required for Newton's method is for us to also know the rate of change. We have to know the derivative of the function. So Newton's method is given to us right here, and we can see that we need the input where we're located, the output, as well as the rate of change. The idea behind why Newton's method works is really simple. All this is going back to your middle school days and thinking about slope as rise over run. Remember that the derivative is equal to the rate of change, and that rate of change of the function is represented with this tangent line here, and its tangent at the point where we are currently located, which is x now and f of x now. That's the point. And all we're going to do is we're going to apply the idea of slope as rise over run. And so what that means for us is the rise is the value of f of x now. Again, why is that true? Well, it's really the difference. It's the difference between f of x now minus 0. It's this distance here because what we are after is the input that gives us a 0 output. And so we take that rise, which is just the function value, and then we divide by slope, which is rise over run. And the result then is the amount of run that we have. What we end up with is we end up with figuring out this change in input values to approximate our input that would give us an output of 0. And of course, that input that would give us an output of 0 is right here. So you can see that in one attempt, we didn't actually find what we were after, but that's okay. What we're going to do is we're going to iterate. We're going to do this process over and over and over again. And so what we're going to do is we're going to take the output that we just got, the x star here, we're going to take this value and we're going to assign that as the new x now. And then we're going to repeat the process. So we can see that this new x now has its own function output here. It has its own slope, which we can calculate because we have that information. And then what we're going to do is end up with another change in the input value. And you can see that we got closer to the input value that gives us 0. So this is what Newton's method is all about. It's about using iteration in order to find or approximate the 0 for a function. So all I have here are both of these graphics. You'll have access to the slides once we get to class. Let's take a look at an example. Let's say we wanted to solve e raised to the power of x over 4 equal to 2. So we can do this using Newton's method. We can rewrite this problem, as we can almost all problems. We can rewrite this as something equal to 0, and we can now define a function f, which would be this left-hand side here, and just set it equal to 0. In this situation, however, it's not necessary. And this is an important part of using Newton's method, is to understand when I do and do not need to use it. So in this case, I can go back to the original equation and simply apply natural log to both sides. And when we do that, we have the natural log of e raised to the x over 4 is equal to the natural log of 2. The left-hand side becomes x over 4, and we can solve for x exactly. So there's no need to approximate using Newton's method. We have the exact calculation right here. Let's pick a different example. Let's say we have e to the x over 4 equal to x. Same approach, we can set this equal to 0, and we can define a function f, which is equal to e to the x over 4 minus x. And we can set that function equal to 0. And that's what we can solve. In this situation, we cannot solve algebraically. So what we want to do is we want to apply Newton's method. First of all, though, pictures are worth 1,000 words. Let's take a look at a graphic here of what we're talking about. The blue plot is e to the x over 4. This tool, by the way, is Desmos. There are a lot of excellent tools out there, as you're well aware, and you should become comfortable using a variety of them. So the problem that we first did was looking at where is e to the x over 4 equal to 2. Well, that would be at this input value right here. And that we already know is 4 times the natural log of 2. We did that calculation directly. In the case where we want e to the x over 4 equal to x, what we're looking for are the input values, this one here and perhaps this one over here. These two places where the two graphs cross one another are where those functions are equal. This is easier to see when we create the function f of x and plot it and look for its zeros. So we're looking for the input that gives us a 0 here, as well as the input that gives us a 0 here. And this is where we can use Newton's method. Let's take a quick look at this from a graphical standpoint, and we can see that if we used Newton's method to try to locate this 0, we can make an initial guess perhaps of just 0, and then we would be up here, and we know what the function value is at that point. We can make that calculation, and we can calculate the derivative, and the derivative would give us some straight line approximation to the function. And then what we would do is we would find our next value, right? So this would become our x star, but that would be the new x now. So we started with x now equal to 0, and that would give us some x star value. And then whatever that value is becomes the new x now. So we set x now equal to whatever this value is, and we go and run this again. And you can see I can't really draw any images here because it gets to be too small. In fact, Newton's method converges really quickly as long as it's stable. And let's say we wanted to find this one over here. You can imagine that we could pick perhaps 8 as our input. And then we have the function output, we have a linear approximation, and then we would come over here and this would be our first x star. And then we iterate. We do this process recursively. So we take the output from the previous step and we feed that in to make it the input for the next step. That's recursion. So let's take a look at exactly how we would line this up. So, of course, for Newton's method, we're going to need the derivative. So I've just calculated the derivative here. Chain rule, which you're familiar with, and you can do this derivative calculation with no problem. So I've put Newton's method up here for reference sake, and I've restated the problem. We're trying to solve for e to the x over 4 equal to x. And of course, we start that by building the function f of x, which we just looked at in Desmos. And we know both the function and its derivative. And remember, we're going to use the input of right now. That's what we're interested in. We start from a value which we call x now, and then we move forward. We won't use that terminology for very long, but that helps to clarify what it is that we're doing. So once we have the function and its derivative, it's time to simply apply Newton's method. And all I've done is substituted the function and its derivative in the correct locations. And now we have something that we put in x now and we get out an approximation x star. So in order to do this calculation recursively, we're going to do it over and over and over again. What we're going to do is we're going to remove the x now nomenclature. We don't want to discuss it that way. We just want to call it x. That's just the value of the input. And we're going to define a function. We're going to define a function where we can put in an x value, and then the output of this function is going to be the input back into the function. And that is recursion. So we're going to take the first output and it becomes the second input. And that's going to give us a second output, which becomes the third input. And we just continue this process until we're satisfied with the approximation for the zero. So this is the idea behind Newton's method. There are a couple of discussion questions which you're going to need to be prepared to address. And let me get out of the way here. So the two questions have to do with recursively using this function that we have created from Newton's method. How exactly is that going to work? And then the other one is, what happens? We talked about finding the zero over here for this function, and we've talked about finding the zero over here. But what happens if our first guess for Newton's method is 5.5? What if we guess right here? What's going to happen? So think about those two questions. Take a look back through the material if you need to, and then we will have a discussion at the beginning of class. Thanks very much, and I look forward to seeing you next lesson.